Good evening, professors and all the faculty members. So, welcome to day one of our 5-day faculty development program on advanced electric vehicle systems and powertrain engineering. So, let us begin with this session. So, on behalf of SkySkill Labs and our academic partners, I welcome all of you again to day one. The major transformation, would say today the automotive industry is ongoing its biggest transformation since the invention of the internal combustion engine. So, God, it has led for centuries. But the next big thing is electric vehicles. So, according to one of the recent industry reports, global EV sales has crossed around 17 million vehicles in 2025 itself. And India is rapidly becoming one of the fastest growing EV markets. Companies like Tata Motors, Mahindra, Hyundai, BYD, Tesla, and VinFast are investing billions in EV technologies. However, before understanding electric vehicles, we must understand how it works or how hybrid electric vehicle works because many modern EV technologies evolved with hybrid systems. So, and as educators or researchers, we have a critical responsibility. The technology our students will work on after the graduation. So, when I talk about after the graduation, it simply means uh, the mobility sector. So the next, electrifications, intelligent energy management, connected mobility, and sustainable transportation solutions. So we are working at, you know, students are evolving or the market is evolving much faster than conventional curriculum. So programs like this will help bridge the gap between academic knowledge and industry expectations. So before we begin, let me briefly introduce SkySkill Labs because I'm sure a lot of you might know about SkySkill Academy or SkySkill Labs because we must have touched at one point. So SkySkill Labs works with universities, engineering colleges, polytechnics, ITIs, and schools across India and internationally to establish industry-aligned laboratories or center of excellence in electric vehicles, renewable energy, drones, embedded systems, IoT, and artificial intelligence. So and emerging technologies also. So our mission is simple: to create a hands-on learning ecosystem that prepare institution and students for future industries. So I'm privileged to have with us Mr. Dipesh Ranjan Singh, who will be leading the first 3 days of this FDP. Mr. Dipesh, is an experienced EV and powertrain engineering professional with expertise in hybrid and electric vehicle systems, battery technologies, simulation-driven development, and powertrain engineering. His work spans around advanced vehicle architectures, battery systems, and industry standard engineering tools, including Ricardo, MATLAB Simulink. He has actively contributed to training engineers, faculty members, and industry professionals in emerging mobility technologies. So before I begin, I would like to ask everyone a question. You can drop down your comments in the chat box. How many of you believe battery technology will evolve faster than motor technology in the next 3 or 5 years? You can share your thought in the chat box. Meanwhile, I'll today's session will establish the foundation of the entire FTP by exploring hybrid vehicle architecture, battery system, and battery management system. So, sir, the virtual floor is yours.
Thank you, Jip, for such a wonderful introduction to the workshop. So I welcome everyone to this workshop. So this is a 5 days workshop. Mostly, I think it is described in the introduction that what are the things that we will be covering in the workshop. I'll directly start with the technicals of the workshop. So here, mostly we will study about the powertrains, the powertrain architecture, powertrain drivetrain architecture of a hybrid electric vehicle. We know that hybrid electric vehicle consists of two kinds of power system. Like there will be a engine, there may be a engine, and there will be a motor. Okay. Like hybrid electric vehicles, some of them may have fuel cells along with motor. They can have or fuel cells along with battery or motor. They can have also engine, okay, with motor. You can also have flywheel technology with motor. Then you can also have other kinds of power systems along with a motor. So when we say hybrid electric, that means motor is common, but along with that, you can have different other kinds of power systems or energy systems. The thing that we will cover in this session, okay, is mostly IC engine, so internal combustion engine along with motor. Okay. We will first cover the theory of what are the types of propulsion used in electric vehicle. Okay. Then we will go for our modeling of those systems. Okay. So the tools that we will be using for modeling is your Ricardo. In Ricardo, we will model the engine. Okay. And in MATLAB, we will model the hybrid architecture. Okay. So I think get the link to download Ricardo. Okay. So that I think is a 3-day session. So in any of the session, like on the next session, I may show you the installation of Ricardo. Mostly I will show you the Ricardo. Okay. It is better if you would do those things afterwards. Okay. So mostly what we will do in Ricardo, we will go for creating the engine. Okay. The type of engine that we want for our hybrid electric vehicle. Once the engine is modeled in here, then we will save the parameters of this engine. Okay, like the torque versus RPM parameters that we will use in our system modeling or in our hybrid powertrain modeling in MATLAB. Okay, there we will also have the characteristics of motor. So we will combine it. So get the links after this, actually after the sessions, or yes, mostly after the session, you will get the links to download the MATLAB and also the Ricardo, practice the models. Okay. So what is a propulsion system? EVs can run solely on electric propulsion or they can have ICE working alongside it. Having only batteries as energy source constitute the basic kind of EV, but there are kinds that can employ other energy source. These are called hybrid EVs. Okay. So the International Electrotechnical Commission Technical Committee proposed that vehicles using two or more types of energy sources, storage or converters can be called as an HEV as long as at least one of those provide electrical energy. So mostly it can have different kinds of energy supply, but along with that it should have a electric energy supply. Okay, then it can be called as a hybrid EV. It makes lots of combinations possible like ICE battery, battery and flywheel, battery and capacitor, battery and fuel cell. EVs can be categorized to battery electric vehicle, full electric, hybrid electric vehicle, ICE running alongside motors, plug-in hybrid electric vehicle. In hybrid here, it is showing that the engine is also charging the cell. So it's a one complete unit. You don't have to have any kind of external charger. You can just charge it from the engine. Plug-in hybrid means you can charge it externally. Most of the hybrids coming now are plug-in hybrids. Okay. So first is battery electric vehicle. That is a full electric vehicle. EVs with only batteries to provide power to the drivetrain known as BEV. BEV also relies solely on energy stored in the battery packs. The range of such vehicle depends on directly on the battery capacity. Typically, they can cover 100 to 250 kilometer in one charge, where the top tier models can go a lot further from 300 to 500 kilometers. These ranges depends on driving condition and style, vehicle configuration, road, climate, battery type, and age. This is age, AGE. Okay, not EDG. This is AGE. Okay, battery type and age. Charging levels of BEV. So this is age. Okay, this is not EGE. Okay, this is right. Okay, I think the annotations are not allowed. Okay, means it is not in the Zoom. Okay, no problem. So this is age, AGE. Charging time of EV depends on the charger configuration, its infrastructure, and operating. Infrastructure means how much kilowatt charger. Okay, 30 kilowatt, 50 kilowatt. Then the configuration of the EV, battery EV, battery, inverter, electric machine, that is a motor, then differential. So it's a full electric. Okay, there is no additional power source. Battery is the only power source. Okay. So same things. Electric propulsion provides instant. Okay. Same thing actually. Then comes your hybrid electric vehicle. Hybrid electric vehicle employ both an ICE and electric powertrain to power the vehicle. The combination of these can come in different forms. HEV uses the electric propulsion where the power demand is low. Okay. So like here in hybrid electric vehicle, there are also two types. That is, there are, you can say high level hybrids, low level hybrids. Okay. High level hybrids are the hybrids in which motor is the main power, you can say main driving source, while engine assists it. Okay, that is high level hybrid. Low level hybrid means you can say engine is the main driving force for the wheel and motor assists it. Okay. So HEV uses electric propulsion whenever the power demand is low. So motor generally consumes low power, okay, as compared to engine. Okay. Because what a 90 kilowatt engine gives you, you can get the same thing from a 30 or 40 kilowatt motor. Okay. So when motor consumes less power, remember, as you are driving an electric vehicle, your energy consumption becomes more efficient. Okay, in your engine, you are actually like if you compare it with an engine vehicle and with an electric vehicle of same size, for four persons, engine or IC vehicles consume more power as compared to electric vehicle because they are less efficient, maximum efficiency. For passenger cars in engine can get up to 45 to 50% max. Okay, 45 to 50%. Okay, so now you can say that. Okay. It also reduces the fuel consumption. When higher speed is needed, the HEV switches to ICE. Okay, so when high speed is needed, because we know that engines provide more torque. That means generally, if you compare a motor torque with engine torque at particular RPM, generally engine tends to provide more torque. So high speed, if it is needed, more acceleration is needed. Okay, at high speed, at low speeds, acceleration motors will, you can say can uh, do the task. But at high speed, if torque is required, engines are required. Hybrid power systems can use extensively to reduce, completely remove turbo lags and turbocharged cars. You can enhance performance by filling the gap. Speed boosts when required. The ICE can charge up the batteries. That means the ICE. This is without plug-in hybrid. Completely on inboard charger. Okay, onboard charger. That means the IC electric. That means the engine will charge the cell. HEVs can also retrieve energy by means of regenerative braking. So hybrid electric vehicles architecture, you can see battery, electric motor, ICE, powertrain. Generally, the motor also acts as a generator. Okay, during starting, you can say the ICE powers the electric motor. Okay, because ICE can power heavily. Okay, remember this is a closed hybrid I'm talking about. I'm not talking about a plug-in hybrid. Okay. Closed means the ICE also charges the battery through the motor. There is no external charger. So starting condition, stopped condition, passing, overtaking. So for overtaking, you need what? More acceleration because there is a vehicle, you are at the same speed, you are overtaking this vehicle. So you need more speed at less time. So you will go for ICE assistance. Braking. Okay. During braking, the motor also charges the battery. That is regeneration and cruising. In cruising, you can say mostly ICE takes over. It also charges the battery, keeping the energy within the vehicle and also runs the powertrain. HEVs are primarily IC driven car that uses electric drivetrain to improve mileage or for performance enhancement. While starting the vehicle, the IC can run the motor as a generator to produce some more power and store it in the vehicle. During overtaking, a boost in speed is required before the IC and the motor gives the powertrain. During braking, the powertrain runs the motor as generator to charge the battery by regenerative braking. While cruising, ICE runs both the vehicle and the motor as generator, which charges the battery. Next comes your plug-in hybrid. Plug-in hybrid means the hybrid that we were talking about. There is no charger. You cannot charge it because the primary driving source is actually the engine. Okay, it is primary. You can see directly connected to the powertrain. Okay, you can see engine is directly connected to the powertrain. Okay, and motor assists it. So it's a low-level hybrid. Mostly your not plug-in hybrids. That means your you can say that as low-level hybrids. Low-level hybrids don't have any charging point. Okay, generally the internal battery pack is charged through the engine only. Okay. But in plug-in hybrids, you can externally charge the cells. Here where comes, that is, if you want to charge your cells now, right? If you want to extend your battery pack uses, you can use plug-in hybrid. Plug-in hybrid concepts arose to extend all electric range for HEV. It uses both IC and electric powertrain like an HEV, but the difference between them is plug-in hybrid electric vehicle uses electric propulsion as the main driving force. In a hybrid where there was no charging point, engine was the main driving force. So it was a low-level hybridization. In a plug-in hybrid, since you can charge the battery pack, that means the motor can be given the task of driving the vehicle, primary task of driving the vehicle. So here this is a high level hybridization. Plug-in hybrids all start in all electric mode, runs directly on batteries are low in charge, calls IC to provide a boost to charge the battery pack. The IC is used here to extend the range. Plug-in hybrid electric vehicles can charge their battery directly from the grid. They can also utilize regenerative braking. Plug-in hybrid electric vehicles' ability to run solely on electricity for most of the time makes its carbon footprint smaller. Chevrolet Volt, Toyota Prius are well-known plug-in hybrid electric vehicles. Then fuel cell electric vehicles. In fuel cell electric vehicle, the fuel cell cannot directly drive the vehicle. Mostly fuel cell is there, battery pack is also there, okay, and motor is there. Motor drives the vehicle. Batteries can be charged externally. Battery can also be charged through the fuel cell. Okay. And fuel cell got the name because the power source of such vehicles are fuel cells that are used chemical reaction to produce electricity. Hydrogen fuel cells of choice for HEB to carry out the reaction, so they are called hydrogen fuel cell vehicles. Fuel cell electric vehicles carry the hydrogen in special pressurized tanks. Okay. You can see here hydrogen cylinders will be there, fuel cells will be there. Okay. Now, why you will see that fuel cell concepts is dying. Okay. Why fuel cell concept is dying? Because hydrogen engines are coming now. You don't need fuel cells. You can directly burn hydrogen just like your petrol. You can directly burn hydrogen and get lots of power, lots of energy. And fuel cell concept is also dying. Why? Because hydrogen cylinders are very heavy to carry. If you don't use dense material to build the cylinders of the hydrogen or build the hydrogen containers, they will leak out. Okay. Now, polymers and other kinds of materials are being used with metal infused matrices. Okay. So that leakage can be prevented. But the fuel cell concept is dying, okay, because of coming hydrogen engines. A hydrogen engine will generate more amount of energy as compared to fuel cell. Why? Because fuel cell generally will run a motor. Motors have all the same kind of graph. That is, initial torque at starting RPM and the torque falls as the RPM increases. Okay. But in hydrogen engines, generally this can be replaced. Hydrogen generates a lot of energy when combusted properly. This helps to generate more amount of energy, and also hydrogen burning of hydrogen is very efficient as compared to burning of a fuel. The outcome is only water. There is no carbon dioxide. So it's also pollution free. So upcoming years, in 10-15 years, you will also see hydrogen engines. Okay. So hydrogen engine along with motor can work. Mostly those type of engines are known as dedicated hybrid engines. Okay. Where you can use both hydrogen and you can also have engine types to use other kinds of fuels. Then, though now we know that the different kinds of power setup that we can have, engine and motor, fuel cell, those power setup creates different types of power flow combination known as series combination, parallel combination, series parallel combination, and complex combination. EVs have different configuration. It can have a gearbox and a clutch that allows high torque at low speed and low torque at high speed, obviously. Mechanical interaction can be further reduced by replacing the motors inside the wheels to produce the in-wheel drive. Planetary gear systems are employed here because of their advantage of high speed reduction ratio and inline arrangement of input and output shafts. So mostly how the power split is done, it is done through planetary gearbox. Okay, we will see a planetary gearbox here where it planetary gearbox can have multiple. Okay, mostly if you are using one planetary gearbox, it can have three inputs and outputs. Okay, you can, if you use multi-stage planetary gearbox, you can have multiple combination of inputs and outputs. This creates this generally this feature of planetary gearbox makes them advantage, or their advantages, or they can say they have lots of advantages to be used in hybrid electric vehicle, because you can connect a motor, you can connect a engine, you can connect a generator directly to a single gearbox. You don't need to have certain kinds of stages if you are using any helical setup, or you are using, you can say, like your what you can say is inline gearbox, or mostly your helical gearbox setup. Okay, mostly helical I will not say. You will say that linear, or you can say that your which kind of gearbox? Okay, your normal gearbox. Okay, normal gearbox means your spur gearbox. Okay, or you can say your compound gear train, not a planetary gearbox. So series parallel hybrid. So first is series. Mostly series hybrid is a, you can say it's a high level hybridization. Okay. You can see the fuel tank generally here. The fuel tank, the power flow, you can see the power flow diagram. Okay. From fuel runs the engine runs the generator runs the rectifier runs the motor controller drives the motor, or you can say drives the wheels. And also through a backup path, the rectifiers, or sorry, the rectifiers also go to DC to DC converters, also charge the battery. The battery can also run the motor. Okay, you can see that from your generator directly battery charger input can also be provided. So why this is a high level hybrid? It is because you can see that motor is directly taking part in driving the vehicle, and engine is assisting the motor in driving the vehicle. Okay. Engine is assisting the motor in driving the vehicle. What is the advantage of this kind of system? You can see that the advantage includes efficient and power optimized plant, possibility of modular power plant, optimized driveline, possibility of swift black box service exchange, long running time, mature technology, fast response, zero emission. Large traction, you can disadvantages large traction drive. Traction drive means your motor, okay, is required, okay, because only motor is taking part in driving the system. So you need large traction drive, okay, or motor. Requirement of proper algorithms to drive the motor, multiple energy step conversion. You can say energy to generator to rectifier to controller to traction motor to mechanical transmission. Again back to battery packs. Series hybrid, generally your high level hybrid systems. Then parallel hybrids. Okay, and you can see the power flow. In series hybrid, the inner engine cannot directly take part in driving the motor. Okay, it cannot take part. It can only assist the motor in driving the vehicle. But in a parallel, it can be both high level and low level. Okay. You can see here engine is directly taking part in driving the system. And traction motor is also driving the system. How this is possible? It is possible by using planetary gearbox. In planetary gearbox, the same input can also act as an output and output can also act as a input. Okay. You can have multiple combinations of power flow in a planetary gearbox. Okay. Okay. So this configuration connects both the ICE and motor in parallel to the wheels. Either one of them or both take part in delivering the power. It can be considered as an IC engine vehicle with electric assistance. Okay. So you can see this is as a low level. Okay. But can also be a high level. Why this is a low level? Sorry. Why this is a high level? Oh, sorry. Low level. Why? Because engine is also taking part. Okay. With electric assistance. That means in electric motor is assisting the engine. That means it's a low level hybrid. The energy stored in such vehicles can be powered by the electric motor through regenerative braking or by IC while it produces more than the required power than the drive wheels. Okay. You can see the engine through the mechanical coupling can also drive the traction motor, can also charge the battery. The motor can also run along with the engine to increase the power output in the vehicle. Advantages capable of attaining zero emission, economic gain, and it is very much flexible as compared to other systems. Okay. Now this is parallel. Okay. You cannot have series in it. It is parallel. Okay. Like the mechanical coupling is set in such a way that is you cannot have series drive. You can only have parallel drive all the time. Then how to have a series drive then? And yes, what are the disadvantage of this kind of system? Expensive, complex control, requirement of proper algorithms, need for high voltage to ensure efficiency. Then comes your series parallel hybrid. Here you can have read here and carry here. Okay. You can see that it sometimes rotates quickly, sometimes slowly. Okay. So you can see this is a planetary gearbox. Generally, you can connect multiple inputs and outputs in here. Okay. You can have, you can connect multiple inputs and outputs. Planet gears, rain gear, and carrier. You can see that it's up. Okay. So you can see that how it is connected. If you see how it is connected, generally this is your, you can say, motor. Okay, this ring gear is connected to the main driving motor that will be connected to the wheel. Okay, planet gear, here the engine will be connected. Okay, in the planet gear generally the engine is connected. Okay, and in the sun gear generally your generator is connected. Okay, sorry, I'm not able to write. Okay, because the annotations are not available. Okay, so generator. Okay, sorry. Okay, M1 means your motor, main driving motor. Then the planet carriers are connected to the engine and the generator is connected to the sun gear. Okay. This is how your planetary gearbox setup is. Now we can have multiple, like we can run the engine keeping the generator fixed. That generally will increase the output of M1. Okay. Let's play it a little bit more so that you can know.
Sometimes rotates quickly, sometimes slowly, and sometimes even in reverse.
Okay. So
But how does this happen?
this happens. So we will see this. We will see this in our MATLAB session. That is how the planetary gearbox will help us. So now when we connect the planetary gearbox, now we can use the engine to help the or assist the motor to run the drive. We can also use the engine to run the generator to charge the battery. We can also use the generator to run as a regeneration unit to charge the battery. We can also use the motor and the engine to drive the system. Okay, we can have multiple types of combinations, like the series combination and also the parallel combination. Like series means we can use the engine to run the generator to charge the battery to drive the motor to drive the wheels. Engine, sorry, series. Parallel means we can also use the engine and the motor to drive the wheel. Okay. And the generator will be fixed at that point. Okay. And drive the system. This is series. So we are getting both series and parallel combination in. Then series parallel hybrid, less complex alternative to this system is used transmotor, which is floating stator electric vehicle. Okay. Another kind of series hybrid can also be done by using a floating stator motor. Okay. Floating stator means actually this is mostly this one. Okay. Like what happens is uh, I'll just give me 1 minute.
Sir, you're not audible.
Just 1 minute.
Meanwhile, sir rejoins with his PPT and all. Just a little announcement. We will be ending this session half an hour early because there was a mistake from our end in the Zoom call. There are a lot of participants who are trying to join, but due to the limit of 300, they are unable to join this call. So we are trying to schedule this tomorrow. There will be 2.5 hour session tomorrow, starting from 6 to 8:30. So requesting your patience, thus we'll complete the session within the next half an hour, and we'll continue from tomorrow. New joining links will be sent over mail. Please keep it checking.
Okay, so you can see these are your dedicated hybrid engines. Okay, so the floating stator motor, you can see inside this one engine, both inside this one casing, both you have both the engine and also the powertrain. Okay, sorry, engine and also the motor. Okay, complete powertrain. So here you have both the engine, motor, and the gearbox. Okay, inside one enclosure. Okay, so this is a dedicated hybrid engine. Okay, generated by Mahel. Okay, it's also available in India and used by most of the manufacturers. This is a dedicated hybrid engine. That means everything is integrated inside one enclosure. Okay, mostly this is the floating stator type. Complex hybrid, you can see in complex hybrid, generally just see the architecture. Engine is there, power split device means one planetary gearbox. Okay. Three inputs, you can see one, two, three. Three inputs and outputs. Connected to another final wheel drive. Okay. Then electric motor generator, again one, two, three. So another planetary gearbox. So here in a complex hybrid, multiple planetary gear stages are used. Inside that hybrid Mahel technology, also multiple planetary gear systems or gear steps are used for, you can say, having to have the complex hybrid. Complex hybrid means you can have varieties of combination in a complex hybrid. Nearly you can have 50, 30, 40 combination. Okay. That means you can directly run from the engine. You can use the generator. Remember, it is written electric motor generator, electric motor generator. Okay. And remember, mostly complex hybrids are used in your four-wheel vehicles. Okay. Four-wheel drive. These are used in your four-wheel drive vehicles. Four-wheel drive means like one, like the main engine will be there, two motors will be there. Both the motors can also act as a generator. Okay. Both the motors can also act as a generator. That is your four-wheel drive system. Okay. So you can run the system from the engine, from one motor, from two motors, simultaneously two motors, okay, or single one motor. You can run in varieties of way. You can have, remember, with two electric machines and two planetary gearbox, you can have 24 ways. If you just add another gearbox, you can have 1,000 different ways of using this system. Okay, that's a complex hybrid system. Then you can have different architectures. So I think most of you got it. What are the different setups that we have? So this, because today is the theoretical session, we will see different setups. In the next session, we'll go for modeling the engine. Then in the next session, we will use our engine and our motor to model the hybrid powertrain using MATLAB. Okay. So since there is a little bit of trouble, like some of the attendees are not able to join. So we will end this session a little bit early. Okay. So I think most of you got about the complex hybrids. Okay. And power split devices. Next comes the motor technology. Okay. That is because without knowing the motor, now we know the powertrain. Okay. Engine is also mostly done. Okay. So we know the powertrain, different series, parallel. Now, what are the different motor technologies that are used? We will cover this briefly. Okay. So what is a motor? Motor is a machine that converts electrical energy to mechanical energy. And motor also acts as a generator. That means it can also convert mechanical energy to electrical energy. It can convert electrical energy to mechanical energy to electrical energy. And there are different features of a motor. Like if you want to select a motor for electric vehicle application, it should have high power. It should have high power, high torque, wide speed range, because your electric drive, if it is in a traffic, it will run at a very slow speed, 20 km per hour speed. During the motor generally heats up at low speed. because lots of current, because it is the architecture. At low speed, motors will have high torque. If you sustain that torque for longer time period, it may damage the motor. So motors should be selected that yes, if this motor can adapt to slow speed and also to high speed. High efficiency, reliability, robustness, low noise, reasonable cost, and small size. With advance of power electronics and control system, different motor types emerged to meet the need of automotive sector. Brushed DC motor, permanent magnet, brushless DC motor, permanent magnet, synchronous motor. See, synchronous motors are the motors that are currently used, okay, in your vehicles because okay, PM BLDC, PM SM. So you can see that we can have different motor configurations in here. So first is your brushed DC motor. Okay. First is your brushed DC motor. Okay. So brushed DC motor. So brushed DC motor, these were the early motors that are used in electric vehicle. Okay. Now these are not used at all. Why early days this was used? Because brushed DC motor tends to generate lot of torque. Why? Because of its construction. It was carrying lots of inertia in it because of its construction. So it was generating a lot of torque. But the engineers got the acute problem of using these motors. That is, since the energy concentration is at the core and the core has a air gap with respect to there is a air gap between the core and the casing. So the heat accumulation is imminent and the heat cannot be removed easily from these devices. So you can say wide speed operation or wide range operation is not available in these kinds of motor. You can see in brushed DC motors, what happens? The core is magnetized, or you can say the rotor. Stator is the outer casing that is static, and rotor that is the one that rotates. Okay. Also, the one that rotates generates heat because winding is there that is supplied with electricity. Commutators are there that heats up because of friction. So these and also the maintenance, these motors also need maintenance. Why? Commutators were there. Commutators tends to wear out, so you have to change the brushes of these commutators, okay, carbon brushes, so that they can continue the operation. So electrification in this motor was good, but other motors showed promising outputs. What kind of motor? Your permanent magnet brushless DC motor. In a permanent magnet brushless DC motor, you can see the rotor is permanent magnet, but the stator has winding. That means when these motors are energized, okay, when these motors are energized, the stator will, like when these motors are energized, the stator, the windings will generate heat. And since the windings are directly connected to the stator and the stator is also exposed to the ambient, so cooling down of this motor is good. Like if your vehicle runs, the vehicle can easily cool down. Why? Because directly there is physical contact between the casing and the wind or casing and the windings. Okay. Not electrical contact, physical. So if the windings heat up, they can dissipate their heat through the stator casing. But in brush DC motor, the winding was at the center, and you can see always there is a gap between the rotor and the stator. Why? Because it has to rotate. So now it cannot dissipate the heat in a brush DC motor, though it has a high torque. But in permanent magnet brushless DC motor, this temperature thing is gone. But it has another problem. What is that? Field weakening. Since it is using permanent magnets, okay, with time the field weakens. So we will take a little break in here. Again, we will join. Hello, Suji, are you there?
Yes, sir. I am here. So we'll take a short 5 minutes break and we'll join back. We have resolved the issue, so we might push it forward. So if you have any queries in the meanwhile, please post it in the chat box so that once the Dipesh sir is back in the group, we can take those questions ahead and we can start with the rest of the session. Are you able to So we can have any questions related to industry, related to recent trends, about the technology itself. Anything would be. I have dropped a question in the chat box related to why do you think hybrid vehicles became popular before EVs or pure EVs? Let me know your thoughts in the comments.
Hello, am I audible? Hello.
Yes, sir.
Okay.
So I have asked a question. Why do we think hybrid vehicles became popular before pure EVs? And I've got a few answers from this. Like efficiency is one of the reasons hybrid vehicles become popular first because they combine the fuel efficiency of electric motors with the convenience of and reliability of gasoline engines due to torque and more speed. So if you could shed some more light on why hybrid vehicles became more popular before pure EVs.
Hybrid electric vehicles, see, mostly they took out one thing, that is range anxiety. Okay. Uh, Mostly urban users, personal users have less range anxiety, but commercial users are facing the range, a lot of range anxiety. Okay. Commercial users means the user those who are driving from, like if you go for a regional manager, okay, he has to drive or he has to move nearly 300 to 400 kilometers per day. So for those people, generally the hybrid electric vehicles become a common thing. Okay, so mostly though they use hybrid electric vehicle. Okay, and commercial, all the commercial electric vehicle, you will see that most all of them will be hybrid. Okay, the technology is already developed. It is just waiting for the right time to get standardized. Okay. Waiting for the right time means obviously the fuel cost, you will see that you can see that fuel cost is high, and it is you can say mostly people will be changing from uh, ICE to battery electric vehicle, then from battery electric vehicle to hybrid electric vehicle, mostly there will be the conversion. Okay, when new types of fuels are also available. Okay. L- Highest lack of charging infrastructure due to battery performance. So they are some of the cases. Okay, but now we can have now we are having batteries that can provide us a range of nearly 800 kilometers in one charge. Okay, for passenger vehicles, for commercial vehicles, generally currently we have 200 kilometers max. But for commercial vehicles, you will see that the hybrid technology will succeed in commercial level. Okay. Okay. So permanent magnet brushless DC motor, the rotor, we know that the heat is being generated in the stator and can be efficiently dissipated to the atmosphere, and the rotor is permanent magnet. But one thing this motors face, that what is that? That is your, you can say, that is your field weakening. Okay. These motors field weakens. Okay. Someone has Manoj Saha, Dr. Manoj Saha has asked, are we really thinking about battery swapping stations as charging infra? What is the main challenge associated with that? Battery swapping is okay. Okay. Like for two-wheelers and three-wheelers, battery swapping is good. Can be scaled, can be managed, the ecosystem can be built. But for more than two-wheelers, for four-wheelers, battery swapping is not a reality now. Okay. So battery swapping is good. Mostly we need that the correct ecosystem for that. Okay, ecosystem means correct GPS tracking. Okay, correct SOC tracking, correct placement of battery swapping structures. Okay, then proper payment gateway. Okay, so all these things, uh, when they become correct, the ecosystem is good, then battery swapping can be easily implemented. Actually, it has to be, it will be implemented. Battery swapping will be the main refueling uh, practice, okay, for two-wheelers and three-wheelers. Battery swapping will be the main, okay, primary, you can say, practice for refueling, okay, for two-wheelers and three-wheelers. It will be there. Okay. Now, when I'm saying generalization, see, I'm not talking about, obviously, we have vehicles where there is no battery swapping working. That type of vehicle will be there. Battery swapping type vehicle will be there. Okay. Okay. So, permanent magnet generally finds itself difficult in the case of field weakening. Okay. DC motor controllers are easier to design than, okay, so we will get all these queries. Let me just complete today's session, then I will come to all the queries. Okay. or it will just slow us down. Next comes your permanent magnet synchronous motor. Now, what is a synchronous motor? When we say synchronous motor, its motor driver is designed in such a way that the PWM frequency that it receives or the duty cycle that it receives, it generates a RPM that is an integral multiple of the duty cycle. Okay, that is why it's a synchronous motor. Okay. Now, what is a duty cycle or PWM? Mostly, we all know how motor drivers run. In a motor driver, you will have three inputs. Okay. Or you can have two inputs. Like there will be a power supply input and there will be a signal. What is a signal? The signal generally says the driver how to switch the motor, how to switch the winding so that it will get a certain output from the motor. Okay. Now, in synchronous technology, generally the synchronous technology was developed to sync multiple motors. Okay. Now, what is this technology? This technology is such that, like, the output, since I cannot write in here, I'll write it on a notepad. Okay. Like if the PWM, okay, frequency, okay, is let's say 60. Okay. 60 kilohertz, or let's say 100 hertz, okay, is the PWM frequency. Then the RPM output of the motor will be integral multiple, like it will be 200 RPM or 300 RPM. So it's an integral multiple of the PWM. Okay. If the PWM frequency is, okay, if the PWM frequency is, let's say 75 hertz, then RPM will be multiple of 75. Okay. That is 150. Okay. RPM. It will be 300. Okay. RPM. So it will be integral multiple. Now, sir, why this helps? It is because if motor 1 PW, because PWM frequency is sent by who? By what? Who generates PWM frequency? Your microcontroller generates PWM frequency, send it to the drivers. Okay, and drivers drive it with respect to the frequency. Okay. Now, if we don't have this proper connection between the PWM and the RPM, then we cannot have sync. Like if motor 1, okay, then sir, how can, like, for sync, what do we need? If let's say motor 1 PWM is 60. Okay. Motor 2 PWM is same 60. Then motor 1 can run at the exact RPM of, let's say, 240 RPM. And motor 2 can also run at the exact RPM of 240. Okay. So they can run in sync because the synchronous is achieved. If I go for an async, okay, that is not synchronous. Async motor generally use voltage. Okay, they use also duty cycle. Okay, but their driver is not sync. Okay, so here if M1 PWM, it's let's say 60 hertz. Okay, M2 PWM is same 60 hertz. Okay, so M1 RPM can be 230 RPM. M2 RPM can be 270 RPM. This is async. That means same PWM frequency, but different RPMs. And sync means same PWM frequency and the RPMs are integral multiple of the frequency. So this can be easily achieved actually. Okay. So synchronous technology means it's a driver technology generally that means even if we have multiple or if we have 100 drivers, if I provide 60 hertz, the driver is going to run the motor at an integral multiple. It is not that fix this RPM, but an integral multiple. Okay. Clear or not? समझ आ रहा है कि नहीं? Hello? Okay. So that is the synchronous technology. Then comes your induction motor. Induction motor means we know that induction motor don't have any permanent magnets in them. They are magnet-free motor. What is the general principle? Magnetic induction. The rotor is a soft iron core. Okay, you can see this rotor is a soft iron core. The stator magnetizes the rotor and controls it. Okay, so the rotor like is not a permanent magnet. So here there is no field weakening. In a permanent magnet, there will be field weakening because permanent magnets can lose their magnetism. But in an induction motor, no one is there to lose its magnetism. It's a soft iron core. It can be magnetized and demagnetized millions of times. Not millions, thousands of times. So induction motors are the first choice of electric drives. But sir, nowadays we are seeing that the permanent magnet synchronous motor is widely used. Yes. Induction motor is used in some electric vehicles, mostly your Teslas use induction motor. Tata Nexon, Mahindra, they all use permanent magnet motors. Why? Because the reliability of a Mahindra's permanent magnet motor is very good as compared to induction motor. So why should you go for a costlier technology? Induction drives is more costly as compared to a permanent magnet motor drive. Okay. Because of what? Because induction motor, you have to control their strategy, your algorithm. The driver is costly. The motor construction is costly. In permanent magnet synchronous motor, the motor construction is easy. The driver design is also easy. Algorithms are also easy. Then comes switched reluctance motor. These are the new kinds of motor. Generally, the working principle is different. What is the working principle of all these motors? The working principle is keep the magnetic field perpendicular to the sorry, keep both the rotor and stator magnetic field perpendicular to each other. Okay, stator magnetic field, rotor magnetic field is always kept perpendicular to generate maximum amount of torque. So in all these motors that we have seen, generally the rotor will follow the stator. Like we will switch the direction of the stator, the rotor will follow the stator, it will follow the stator. We don't want the rotor to align with the stator because the RPM will zero. Okay, so we switch it so that the rotor will follow the stator. But that is not the case for a switch reluctance motor. In a switch reluctance motor, the rotor and the stator both are at 0 degree, not 90 degree. So they use magnetic reluctance. Magnetic reluctance means you know that when two magnets are joined, it is difficult to separate them. That's what happens in here. When we magnetize the motor, the rotor and stator becomes one connected pair. Okay. We don't switch the rotor, we don't switch the stator, so rotor will not follow it. Just the rotor and stator become fixed to a magnetic field. And when we rotate the magnetic field, okay, the rotor rotates along with it. Okay. Okay. The rotor rotates along with it. Okay. So guys, so this brings us to the end of today's session.